So we've seen that the nitro group makes the phenol more acidic. Where would we put the nitro group to get the most acidic compound? In the O, the M, or the P positions?
The O or the P.
That's right, because we were just saying we want this to be close to the negative charge, so we want to put it in the O or the P positions. Let's spell that out a little bit more. Let's say we put the nitro group over here. Well, we know then that there's a resonance structure where the negative charge will be right next to the nitrogen. Well, that already looks good because we want the negative charge to be as close to the nitrogen as possible. But then there's a new resonance structure where the negative charge actually migrates out of the ring. And this can only happen because the nitrogen is right next to the negative charge here. If the nitrogen had been in the M position, we would never get this resonance structure where we kick the negative charge out. This is, so this is a new issue that didn't come up with the chlorine, because resonance isn't very important for chlorine. But this gives us even more reason to want the electron withdrawer at the O or the P positions, because it gives us a whole new resonance structure where we pull the negative charge right out of the ring. If the nitro group had been in the M position, it would never be in a good position to pull the negative charge out of the ring. Let's say we put an alkyl group on the benzene ring. Don't worry about the position for a second. Does the alkyl group make the benzene ring more acidic or less acidic?
It makes it less acidic.
Yeah.
Because it's electron donating.
That's right. We just have memorized that alkyl groups are electron donating. So the alkyl group makes it less acidic. But which of these two pictures would be the least acidic of all? Comparing these two.
The phenol with the methyl in the M position.
This is the least acidic?
Yep.
Why is that?
Well, because on the OH with the methyl in the P position, you're already going to have that's where you're going to find your negative charge anyways in your O and P position. And when you have something there that's electron donating, you're just amplifying it.
Yeah, I think there might have been a mistake there. So if we lose the negative charge, if we lose the negative charge, it will look like this.
Correct.
Now, we can also delocalize the negative charge into the ring.
All right.
Which positions will the negative charge end up on in the ring? It'll be the same answer as in the previous cases. If we do resonance, what positions will the negative charge end up on in the ring? This will be the same as in the previous.
Well, it would be an O and P position.
Yeah, we've seen that negative charges get put into the O and the P positions. Now,
so I'm sorry. Oh, I'm sorry. I was a little confused. The methyl in the P position would be the least acidic. Excuse me.
Because this would put it right next to one of the negative charges, but do we want it to be next to the negative charge? No. This is the opposite of an electron withdrawer. That's why I wanted to briefly talk about this, because we just spent the last few minutes talking about electron withdrawers. So now we have to switch and think about electron donor, and the effects get totally reversed here. Because this is an electron donor, we want to keep it away from the negative charge if we want this to be acidic. So comparing these two, this is less acidic. This isn't quite as bad because there won't be any resonance structures where the alkyl group is right next to the negative charge. There's a resonance structure where the negative charge is here, here, and here. But there would never be a resonance structure where the negative charge is right here. So this is not quite as destabilized, so it's a little easier to lose this proton. So the most acidic case is without having the electron donor at all. But if we have to have the electron donor, it's better to, and we want it to be acidic, it's better to put things in the M position so it doesn't get too close to the negative charge. So certainly on the exam, if you're doing an acid-base problem, I would suggest trying to draw resonance structures to help you think about that. Even if you don't specifically need that to answer, to get credit on the question, that's the thought process that we're supposed to go through. You can expect, you might see some examples in the test that weren't talked about in the book, because you're supposed to be able to figure those out using resonance. What do you think would happen here?
I think that the base would deprotonate the hydroxy, and then the electrons would push them themselves down onto the ring.
Okay, good. So this is actually a pretty simple question. You gave the right answer. What would happen here is just an acid-base reaction. You recognized that this is sodium hydroxide, which is a strong base, and that the hydroxide is just going to deprotonate the phenol. We've just been talking about how phenol is somewhat acidic. So it's simply going to be deprotonated. What happens to the hydroxide? Well, it turns into water. And now since the charge has moved over here, the elegant thing is to draw the counter ion next to that charge. So now we have a sodium phenoxide salt, sodium phenoxide. Now this reaction goes pretty close to completion. This goes to completion, and the reason is, where would the negative charge rather be? On the hydroxide or the phenoxide?
On the phenols.
For the reason you already gave, that this is stabilized by resonance. Now, it's not necessary in this case to actually draw the resonance structures where the negative charge is in the ring, but it's good to know in the back of your mind that they're helping to stabilize this negative charge. So this reaction is favored because the negative charge would rather get from here to here. That's just a simple acid-base reaction. On the other hand, this is what we could call sodium bicarbonate. Here we have sodium bicarbonate. This is a base, but it's not a strong base. And so it looks like you should know that this is not strong enough to deprotonate the phenol. Most phenols do not react with weak bases, such as sodium dicarbonate. So for the most part, we'll get no reaction here. Maybe there'll be some deprotonation, but not very much. This reaction favors the starting materials, whereas this reaction favored the products. This just comes back to what we said before. Phenols are more acidic than normal alcohols, but they're still not real acids. This is still not that acidic. It takes a strong base to deprotonate it. Now, another point here is when this got deprotonated, did it become more or less soluble in water? This takes us back to something we talked about a few weeks ago. We talked about when do things dissolve in water and when don't they.
It becomes more soluble.
That's the right answer. This is soluble in water. What is it about this that makes it so soluble in water?
It's polarity.
Yeah, and what makes it polar? The charge. We talked a while ago when we talked about extraction. Remember that like dissolves like. Well, water is a very polar solvent because it can do hydrogen bonding. Water is a very polar solvent, so polar solutes dissolve best in it. So something with a charge is going to be very soluble in water. However, the starting material here was not that soluble. Even though this can do hydrogen bonding, that's outweighed by all these nonpolar carbons over here. So this has both a polar and a nonpolar region, but these 6 nonpolar carbons over here would tend to make this relatively nonpolar. So this would not dissolve in water very well. Relatively insoluble. So the point here is, if you treat phenol by itself doesn't dissolve in water that well. If you treat phenol with sodium hydroxide, will it dissolve in water then?
Yes.
Because it becomes a phenoxide salt. If you treat phenol with sodium bicarbonate, would it dissolve in water?
No.
Right, that's the key thing it looks like your instructor wants you to know about this. And why do we care where it dissolves? Well, we saw that that is important if you want to do a separation, say. If you want to do a separation using the extraction method, we talked about how it's convenient that some things might become polar and some things might not.